Welcome to Homework Lib.
This is chapter 35, problem number 42. We have a brass plate that has slits on it. Is being heated up. So, of course, when the metal is heated, it will expand from its initial width to a different width. We're going to prove that it actually expands. Now, for the destructive interference to happen, that it happens at the sine theta equals lambda over 2, as you know. And also, like we said, the metal, when it's heated, it's going to expand. So while though instead of this d, this distance between the slits, I suggest that we use something else, because we're going to do differential work where we might get confused from the differential d to the d between the d and the slit distance between the two. So I was going to suggest that maybe we should use something like w width. So then we can rewrite this equation as with sine theta equals lambda over 2. And now from the expansion, this is differential width is going to be changing with respect to this lambda, which is the coefficient of expansion, from the initial width of the initial width with respect to temperature, right? So then if we go back here in this equation, isolate sine theta, then it's going to be lambda over 2 omega, or w. Now, if we take differentials of both sides, then it's going to be cosine theta d theta lambda over 2, as you know, the differential of 1 over w. So 1 over omega, I'm going to call it. So lambda over 2 is going to be equal to negative 1 over omega square d omega then. So let's rearrange everything here. 1 over omega squared, lambda over 2 d omega. Now we can plug the omega in this equation so that what we have is negative 1 over omega squared, lambda over 2. For d omega, we have alpha omega naught dt. Oh, well, we're going to cancel 1 omega out. So we're going to have lambda over 2 omega naught alpha dt. For, again, the left-hand side of this equation is cosine theta d theta. And now let's go to the next page. Then d theta, if I isolate d theta, I'm dividing both sides by cosine. Negative alpha lambda over 2 omega naught cosine theta naught, right? These are the initials dt. So now omega naught sine theta naught is going to give us lambda over 2 from the first equation. Then from here, lambda, we're just applying the initial values, right? Boundary conditions. So sine theta naught. Then if you plug this in the equation, we can write d theta in terms of 2 omega naught sine and theta naught over 2 omega naught cosine theta naught dt. So 2 omega naughts are going to cancel. Negative alpha sine theta naught over cosine theta naught. Let's just write this as tangent theta naught, right? Tangent theta naught dt. So from there, well, actually, we can go back to, if you will, so delta theta, basically, this equation equals negative expansion coefficient tangent of the initial angle and delta t, right? So this is our equation. Delta T, we know that the initial room temperature, the final is 135 Celsius. Even in Kelvin, delta T wouldn't change, right? So delta theta is we can look up what this expansion coefficient is. It's 2 times 10 to the power of -5 inverse of Kelvin. Now tangent of the angle that is given to us as 26.6 degrees. Delta T then is going to be 135 minus 20, which is 115. 115 Kelvin. Even if you convert it to Kelvin, the difference is not going to change. So then we find delta theta to be negative, first of all, 0.00115 radians. This negative sign here has an importance. That means the brass expands, so the slits get away from each other. Okay, slits get away from each other. Then actually that causes the fringes to get closer together. Then fringes get closer together. That's what this negative sign means.